Okay, let's move along and get into section 6.5, rational functions and rational equations. You see, I like to abbreviate those big long words. On page 478, rational function is defined like this. F of x is a rational function if it is one polynomial divided by another polynomial, right? It's the ratio of two polynomials. Let's look at example 1. This, in fact, is a polynomial function. X plus 1 is a polynomial, and quantity x plus 2 squared is a polynomial. Let's see if we can figure out what the graph of this looks like. Now recall that we have looked at a real simple rational function before. Several weeks ago, we graphed y equals 1 over x. This is a rational function. They're both polynomials, 1 and x. 1 is the simplest polynomial you could possibly have. It's just a constant. And we recall that the graph of the function looks like this. These two curves, two pieces that don't touch each other. And they both get infinitesimally close to the y-axis, but they never touch it. So that's called a vertical asymptote, which we normally abbreviate with VA. And we see that q of x would be 0 here if 0 was allowed in the domain. Of course it isn't, because 0 makes the domain, well, you'd be trying to divide by 0, and that's impossible. And at the same time, p of x is not 0. That's the other requirement. To have a vertical asymptote, you have to have p of x be non-zero, where q of x goes to 0. So we expect to see some effect like that, at least if we have a vertical asymptote. Let's see if we have a vertical asymptote. We set the denominator equal to 0 and solve, and we see, yeah, at x equals -2, this function is not defined. We'd have to be dividing by 0. Meanwhile, x plus 1 at -2 does not equal 0. In fact, it equals -1. So we've got a vertical asymptote, and I drew this dashed line to indicate it here. What's the rest of the behavior going to be like? Well, I'd expect to see two different curves, two different pieces like that. Let's see if we can plot some points and see that effect, see those curves, and figure out what this looks like. So over here I have picked a bunch of x values and computed the y values. So when x is -1, we actually have our x-intercept. When x is 0, here's our y-intercept. Y would be 1/4. When x is 1, it's 2/9, which is slightly less than 1/4. When x is 2, it's 3/16, which is slightly less than 2/9. And they're going to keep getting lower and lower as we move along. So this part of the curve has a little hump there, and then it gets lower and lower. Now here, it's going to continue on and go through the x-axis right there. If I plot these points, -3/2, -2 would be there. -5/2, well, that's on the other side of the x-axis. We could plot some more points and you'd see we're getting the vertical asymptote right there. We have that asymptotic effect. What happens over on this side? If I plot -5/2, then I get -6. I'm way down here. If I were to plot -3, x equals -3, I'd get -2. And if we plotted a few more points, you'd see that we have this familiar shape here. So that's sort of your standard way for plotting a rational function. Now, just take a quick look at problem number 7 on page 487. So that's number 7, page 487. You're just asked to look at 4 rational functions and find out which one does not have a vertical asymptote. Okay, how did you make out? Let's get this stuff off the board first. In problem number 7, in part A, you're given the function f of x equals x minus 3 over x squared minus 4. So we want to set the denominator equal to 0 and see if there's a vertical asymptote. I see that I get 2 solutions to that, plus or minus 2. So I see that this function has a vertical asymptote at x equals 2, and it has another one at x equals minus 2. So this is not the function we're looking for. We're looking for the one that does not have the vertical asymptote. In part B, the denominator of the rational function is x squared minus 4x equals 0. I quickly start to solve it, and I never finish solving it, but I can see right here like, oh, there are solutions to this equation, so this has a vertical asymptote. In fact, it has 2 of them. So no, that's not a function that does not have a vertical asymptote. Let's look at part C. Here the denominator of the function is x squared plus 6. So we set it equal to 0. I get x squared equals minus 6. I say, ooh, there's no real root. Of course, now we're only graphing functions on the real number lines, right? We don't graph functions that take non-real numbers, that is to say, complex numbers. So this has no real root, so it has no vertical asymptote. So yes, this is the function that we're looking for. And just to double check, if you look at the denominator in part D, you can see it's already factored for you. You can see, oh, this has a couple of real roots, so therefore it has a couple of vertical asymptotes, assuming that these real roots don't cause the numerator to go to 0 at the same time. Okay, so that's how you work with vertical asymptotes. On page 480, let's go ahead and look at horizontal asymptotes. We briefly mentioned this in the past also. Now we'll cover it a little more thoroughly. On page 480, we have this piece of information about horizontal asymptotes. If y approaches a number a, and I'll just use the arrow to indicate approaches, as x approaches infinity, either positive infinity or negative infinity, so that is to say, as x goes to negative infinity, we're looking to the left on our graph. As x goes to positive infinity, we're looking to the right on our graph. If this happens, then the line y equals a is a horizontal asymptote, abbreviated HA. Now it gets a little more complicated. Let's consider our rational function again. F of x equals p of x over q of x, where p of x and q of x are polynomials. Now, these polynomials are going to have some degree. Let's say that the degree of p of x is n, and let's say that the degree of q of x is m. Well, that means that p of x looks something like this. A sub n times x to the nth plus a sub n minus 1 times x to the minus 1, and so on and so forth all the way down to a sub 0. And that means that q of x looks something like this. Let's call its coefficients b. So we have b sub m multiplying x to the power mth, to the power m, the mth power, plus b to the sub m minus 1 multiplying x to the m minus 1, so on and so forth, down to b sub 0, which would be the constant coefficient. So on page 41 here, you see that there's 3 rules for determining what the horizontal asymptote would be if it exists. First thing that can happen is m is a greater number than n. If that happens, that means the degree of q of x is greater than the degree of p of x. That means the horizontal asymptote is the x-axis. The horizontal asymptote is the line y equals 0. The second thing that might happen, they could be equal. If that happens, there is also a horizontal asymptote. And it's the line, the horizontal line, y equals a sub n divided by b sub m. In other words, it's the ratio of the lead coefficients, right? The lead coefficient of the top polynomial divided by the lead coefficient of the bottom polynomial. The third thing that can happen is n is greater than m. Right? The degree of the numerator is greater than the degree of the denominator. If that happens, there is no horizontal asymptote. So let's have you all work one out here to make you more familiar with these ideas. On page 487, do number 2. You're asked to find vertical and horizontal asymptotes for a rational function.